Hello, my name is Kevin Craig. I have created 12 modules on electronics and measurement for mechatronics. Modern engineering practice requires that engineers model, analyze, and predict before they measure. What is mechatronics? The diagram you see I created in 1995 as a professor at Rensselaer Polytechnic Institute. It is used throughout the world to represent the field known as mechatronics. Mechatronics is multidisciplinary systems engineering. It is the synergistic integration of physical systems, electronics, controls, and computers through the design process, from the very start of the design process. These modules present the fundamentals of electronics and measurement for mechatronics. This is Module 7 on operational amplifiers, op-amps. Topics covered are an introduction, op-amp characteristics, real op-amp versus ideal op-amp, open loop gain versus closed loop gain, the inverting op-amp, negative feedback, trans-resistance amplifier, non-inverting op-amp, unity gain buffer op-amp, difference and summing amplifiers, non-inverting summing amplifier, differentiator and integrator op-amps, active lead lag controller, transconductance amplifier, and active low-pass filter. Introduction. An operational amplifier, op-amp for short, is a voltage amplifying device designed to be used with external feedback components, resistors and capacitors, between its output and input terminals. The configuration of these feedback elements determine the resulting function or operation of the amplifier. For example, filtering, control, mathematical operations. A typical op-amp has 5 pins, a non-inverting input, an inverting input, an output, and 2 power supply pins, one for plus voltage, one for minus voltage. The relationship between the output and the input is that Vout equals some gain A times Vin, where Vin is the non-inverting input V1 minus the inverting input V2. So the op-amp is a 3-terminal device, inverting input plus, non-inverting input minus, and output. The output is the difference in the 2 inputs multiplied by a gain A. In addition, there are 2 input power terminals. There are 4 classifications of op-amp gain: voltage, in and out, current, in and out, voltage in and current out, called transconductance, and current in and voltage out, called trans-resistance. The operational amplifier is possibly the most versatile linear integrated circuit used in analog electronics, for example, for filtering, signal conditioning, and math operations. It is a voltage amplifier. The op-amp is strictly not an element. It contains elements such as resistors and transistors. Here is a schematic of the LM741 op-amp showing the transistors and resistors that are integrated in this op-amp. However, the op-amp is a basic building block, just like resistors, capacitors, and inductors. We treat this complex circuit as a black box. It looks like a black box. Here is the 741 op amp, a black box with a notch to show its orientation, and 8 legs or pins. Do we need to know all about the internal details? Absolutely not. Do we need to know how to use it and interface it with other electronic components? Yes, we must. Here is a diagram showing the pinouts of the 741 op amp. Pins 1, 5, and 8 are usually not connected. Pin 3 is the plus or non-inverting input. Pin 2 is the minus or inverting input. Pin 6 is the output. Pin 4 is the negative voltage supply. Pin 7 is the plus voltage supply. Op amp characteristics. As an ideal amplifier, it has infinite gain and bandwidth when used in the open loop mode, typical DC gains of over 100 dB. That's 100,000. The basic op amp construction is a 3-terminal device, 2 inputs, a plus and a minus, and 1 output. And that's excluding the 2 power connections. The op amp can operate from a dual power supply, for example, plus or minus 15 volts, or from a single DC supply voltage. The ideal op amp has infinite input impedance, 0 output impedance, and instantaneous response. The 2 golden rules for ideal op amp behavior are that there is no current flowing into either of its 2 inputs, plus or minus, and there is 0 input voltage difference. That is V plus equals V minus. An op amp senses the difference between the input voltage signals, V plus minus V minus, and then multiplies it by predetermined gain A, called the open loop gain. Closing the open loop by connecting a resistive or reactive component between the output and the inverting input reduces gain A, but it makes the op amp stable, predictable, and insensitive to variation in A. That is negative feedback. Open loop gain A and bandwidth. Both are infinite for an ideal op amp. The main function of an op amp is to amplify the input signal, and the more open loop gain, the better. Open loop gain A is the gain of the op amp without feedback. For an ideal op amp, the gain is infinite. For a real op amp, the gain ranges from 20,000 to 200,000. The open loop op amp has a frequency response with a bandwidth that is infinite for an ideal op amp, but appears like a first order system response for a real op amp. For example, here is the transfer function for a first order system with a gain of 100,000 and a time constant in seconds of 0.0159. The bandwidth is 1 over tau in radians per second. If I then divide that by 2 pi radians per cycle, I get hertz, or in this case, 10 hertz as the bandwidth. And that's the point where the amplitude drops minus 3 dB from the low frequency value. The frequency where the open loop op amp gain is unity, here we see that here, it intersects the frequency axis at 10 to the 6th hertz, where the gain is 0 dB, or 1. The frequency where that open loop op amp gain is unity is called the gain bandwidth, dB. Along the curve, the product of gain A and frequency in hertz is a constant. Here it is equal to 10 to the sixth. So at any point, the gain and the frequency multiplied together give us 10 to the sixth. Bandwidth is inversely proportional to gain. And the slope of this line we see for a first order system is minus 20 dB per decade, where a decade is a 10 to 1 frequency change. Input impedance, Zin. It's infinite for an ideal op amp. Input impedance is the ratio of input voltage to input current and is assumed to be infinite to prevent any current flowing from the source supply into the op amp circuitry. That is, In equals 0. Real op amps have input leakage currents from a few picoamps to a few milliamps. Output impedance, Zout. Ideally, it is 0. The output impedance of the ideal op amp is assumed to be 0, acting as a perfect internal voltage source with no internal resistance, so that it can supply as much current as necessary to the load. This internal resistance is effectively in series with the load, thereby reducing the output voltage available to the load. Real op amps have output impedances around 100 ohms. Offset voltage. Ideally, it is 0. The op amp output will be 0 when the voltage difference between the inverting and non-inverting inputs is 0. Real op amps have some amount of output offset voltage. Here is a schematic of a real op amp with our non-inverting input V2, our inverting input V1, Vin is defined as V2 minus V1, our input impedance, which is approximately 2 mega ohms, an output voltage with a transfer function equal to A times V2 minus V1, or Vin, over tau S plus 1. A is about 200,000 and very unpredictable. Tau is about 1 microsecond, very fast, but not infinitely fast. And Zout is about 75 ohms. This is a real op amp. An ideal op amp has infinite input impedance, and therefore currents I1 and I2 are 0. Tau is equal to 0. Here tau is very small, but it's not 0. Ideal op amps have instantaneous response. Zout is 0. The output impedance is 0. Here it's small, 75 ohms, but not 0. For an ideal op amp, Vout equals A times V2 minus V1. A is infinite, therefore V2 equals V1. And the output must stay between the supply voltage values, minus V supply and plus V supply. Open loop gain versus closed loop gain. We've seen a diagram of the open loop gain for the op amp in dB versus frequency. It's shown here in this blue curve. This is the bandwidth, this is the breakpoint, and this slope is minus 20 dB per decade. At 0 dB, the value of this frequency is called the gain bandwidth. It's the amplitude of our op amp. In closed loop operation with negative feedback, the gain, whether high or low, and here it's shown for a inverting op amp with negative feedback, where the gain, as we will see, is the ratio of the feedback resistor divided by the input resistor. Here it is high, here it is low. But at a frequency, that gain can never exceed the open loop gain. So once we get to a frequency where this horizontal line runs into the open loop gain, the gain then will follow the open loop gain curve. We see another diagram over here to further explain the relationship between the open loop and closed loop gains. This is an inverting op amp. The op amp has negative feedback. The non-inverting input V1 is connected to ground. The inverting input V2 is connected through a resistor Rin to Vin. The output voltage is connected through a resistor R feedback to the inverting input terminal. Applying the ideal golden rules, which tell us that no current flows into the input terminals, and the differential input voltage is 0, which means that V2 equals V1, results in a relationship V out over V in equals minus R feedback over R in. If R feedback equals R in, we then have a unity gain inverter or inverting buffer, as V out would equal minus V in. This is an inverting op amp. My gain is A. The non-inverting input is connected to ground. The inverting input is connected through R in to V in. The output voltage is connected through R feedback to the inverting input terminal. I know that V out equals A times V1 minus V2, which is minus A times V2. This is for an ideal op amp. Since the current flowing through R in must be the same as the current flowing through RF, as no current can flow into the op amp, V in minus V2 over R in is I in, V2 minus V out over RF equals IF, and these two must be equal. After some algebra, I get this relationship. If I look at a negative feedback system, in this case V in and V out, where K is the element in the forward path and beta is the element in the feedback path, and I have negative feedback, the minus sign here is because of the inverting op amp nature, but the output over the input, according to my feedback block diagram relationships, equals K over 1 plus K times beta, which if beta K is much, much greater than 1, this is approximately equal to 1 over beta. Now, if I substitute what I found in my inverting op amp relationship into this formula, I find that K is equal to A times R feedback over the sum of R feedback plus R in. And beta is equal to R in over R feedback. And beta K equals A times Rin over R feedback plus Rin. So I see that if beta K is much, much greater than 1, meaning that A is very large, then minus V out over V in is approximately equal to 1 over beta, where beta is equal to Rin over Rf. This is an ideal trans-resistance amplifier. Current in, voltage out. The input current is from some photo device, and the device is connected to the inverting input. I have negative feedback from V out through a feedback resistor to the inverting input. The non-inverting input is connected to ground. Again, this is an ideal op amp. V out will then equal minus the source current times R feedback. This is a non-inverting op amp. V in is connected to the non-inverting input. V out is connected to the inverting input through the feedback resistor R sub F. The inverting input is also connected to ground through the resistor R2. We see that since the non-inverting input and the inverting input for the ideal op amp must be the same, if V plus is V in, then V minus must be equal to V in, or here V1 is equal to V in which case I have a voltage divider. Voltage divider analysis will show that V out over V in is equal to 1 plus the ratio of the feedback resistor to R2. Unity gain buffer op amp, or voltage follower. We just analyzed the non-inverting op amp, where V out over V in is equal to 1 plus the feedback resistance divided by R2. If I let the feedback resistance be 0, and I let R2 be infinite, meaning this is an open circuit and this is a short circuit, then V out over V in is 1. And this is what we call a unity gain buffer op amp, or voltage follower. This is an ideal differential op amp. V out is equal to R feedback over R in times V2 minus V1. In this case, the feedback resistors must be matched. The input resistors must be matched. This is a summing op amp. It's inverting. V out is equal to minus the ratio of Rf to R1 times V1 plus the ratio of Rf to R2 times V2 plus the ratio of Rf to R3 times V3. That sum with a negative sign, as it is inverting. This is a non-inverting summing amplifier. We have V1 and V2 as inputs, each with current flowing through R1, current flowing through R2, summed together, which must equal 0, as no current can flow into the op amp. So IR1 is V1 minus V plus over R1. IR2 is V2 minus V plus over R2. And these two expressions added together must equal 0. As this is an ideal op amp, V plus is the same as V minus, and with the resistors RA and RB form a voltage divider, where the gain of the op amp is 1 plus RA over RB. If R1 equals R2 equals R, and RA equals RB, then we see that V out equals V1 plus V2. A benefit of this op amp configuration is that it has a much higher input impedance than the inverting summing amplifier. This is an ideal differential amplifier. V1 is connected through resistor R1 to the inverting input. V out is connected through the resistor R3 to the inverting input. V2 is connected through the resistor R2 to the non-inverting input, and the non-inverting input is connected to ground through resistor R4. Applying the ideal op amp golden rules, we see that the current flowing through R1, I1, must be equal to the current flowing through R3, which is IF. And VA must be the same as VB, and VB is related to V2 through the voltage divider relationship. Performing the algebra, we get this relationship for V out as a function of inputs V1 and V2. If R1 equals R2 and R3 equals R4, then V out is equal to R3 over R1 times V2 minus V1. This is the differentiator op amp. It is an inverting op amp where Rin has been replaced with a capacitor. The formula for the inverting op amp still applies, not just for resistances, but for any impedances. Substituting in for C, its impedance, which is 1 over CS, where S is the differential operator, we find that V out is minus R feedback times C times the derivative of the input voltage. This is the integrator op amp. Again, this is an inverting op amp, ideal, where the feedback resistor has been replaced by a capacitor, replacing the capacitor by its impedance, 1 over CS, again, where S is the differential operator. We then get V out is equal to minus 1 over Rin times CS, or D, where we have replaced S with J omega for frequency response. So this is the relationship between V out and V in, where now you're integrating V in to get V out. This is an active lead lag controller. This is an inverting op amp where in the feedback path we have the parallel combination of R2 and C2. And in the forward path, we have the parallel combination of R1 and C1. Using ideal op-amp golden rules, E out over E in is minus the impedance in the feedback path divided by the impedance of the input path. The result is what I have shown here. Depending on the values you choose for R1, C1, R2, C2, you can get lead or lag analog control functionality. This is a transconductance amplifier, or a voltage to current converter. The voltage at the non-inverting input by voltage divider is equal to E in times R2 over R1 plus R2. The non-inverting voltage must be the same as the inverting voltage, which then must be the voltage at this node. Any current that flows from the output through my LR circuit, which I represent an electromagnet with, any current that flows through this must go through the sampling resistor RS, as no current can flow into the op-amp. So I see that the current flowing through my electromagnet and then through the sampling resistor is equal to the voltage divider ratio times 1 over RS times E in. And this assumes ideal op-amp behavior. Let's consider the non-ideal op-amp behavior of the transconductance amplifier. E in is related to the non-inverting input through the voltage divider made up of R1 and R2. E out is related to the current flowing through my LR circuit, my electromagnet, by the relationship E out minus E1 is equal to LMS plus RM times that current. The current flowing through the electromagnet cannot flow into the op-amp, but must flow through the sampling resistor. So E1 is equal to R sampling times the current. We're using a non-ideal model for our op-amp where E out is equal to A, which is very large but not infinite, over tau S plus 1, where tau is very small but not 0, times E plus minus E minus. If I combine all of these terms, I see that E out minus E1 is equal to LMS plus RM times I, but I is equal to E1 over R sub S. Factoring out E1, I get the relationship between E out and E1. So creating a block diagram to represent these equations, I see that E out times this ratio gives me E1. E1 times this ratio gives me I from this relationship. Then this voltage here, E plus, which is E in times the voltage divider ratio, minus the inverting input, which is E1, times my non-ideal op-amp transfer function, A over tau s plus 1. The saturation block is meant to show that the voltage is limited to within a small fraction of the plus or minus supply voltages, meaning that the output cannot exceed the plus or minus supply voltages of the op-amp. This then is the transconductance amplifier non-ideal op-amp behavior analysis. Here is an active RC low-pass filter. My situation is that I have a signal with a frequency of 1 hertz and an amplitude of 0.2 volts peak to peak that I want to measure. However, there is a 60 hertz noise signal that has a peak-to-peak voltage of 0.1 volts. I need to filter out the 60 hertz signal while still recording the 1 hertz signal without much attenuation, 5% attenuation at most. So I want the output to be 1 hertz with a peak-to-peak voltage of no less than 0.19 volts. But I'd like to attenuate the 60 hertz signal from 0.1 volts peak to peak to 0.005 volts peak to peak. If I design this low-pass filter, I find that RF times C is equal to 0.053 seconds, and Rin equals RF. My active low-pass filter, and it's active because of the op-amp, has a potentiometer for my input resistance, a potentiometer for my feedback resistance, and of course my capacitor. These are the values for C, RF, Rin. Ideal op-amp assumptions lead to this result for my transfer function. So you see that I can set the time constant for my low-pass filter, RF times C, by a choice of RF and C, but I can set the input impedance of my low-pass filter by a choice of the combination RF and Rin. Let's verify our design in hardware. Here is my workstation. You see my multimeter, my digital oscilloscope, waveform generator, and assortment of power supplies. And here is my breadboard. On the breadboard, I have built the LM741 buffer op-amp unity gain configuration just to show how it is breadboarded. Here is my active low-pass filter with the 741 op-amp, with my input resistance made up of a fixed resistor and a potentiometer, as I show here. The feedback resistance is made up of a fixed resistor and a potentiometer, as I show here. The capacitance value is fixed. You also see that I have a 1 microfarad electrolytic capacitor and a 0.01 microfarad ceramic capacitor, and this is for noise suppression on both voltage supply rails. I see that at 1 hertz, if I input a 1 hertz signal, I see on the oscilloscope that the ratio of the output to the input is 0.943. My design goal was to have that ratio be equal to 0.95. At 1 hertz, the phase lag is 18.66 degrees, which translates into a time delay of 0.052 seconds. So implementing a filter does have this drawback. Here I have performed a step response test and shown that for this active low-pass filter, that at 63% of the steady state value, the time constant is 0.054 seconds. At 3 hertz, which is the bandwidth for my active low-pass filter, that's the frequency at which the amplitude ratio drops to 0.707 of its low frequency value, I find that the amplitude ratio is very, very close, 0.717, and ideally the phase angle should be minus 45 degrees, which it is very close to. And at 60 hertz, where I want an attenuation by a factor of 20, my output to input voltage ratio is 0.088. So all things considered, this RC active low-pass filter meets my design specifications. Here is the Bode plot for my active low-pass filter. Here we can see how at high frequency it approaches minus 90 degrees, where the high frequency slope is minus 20 dB per decade. And we can identify the time constant from my Bode plot. And this is done with the National Instruments MIDAC Bode plotter. This concludes the module on op amps. Thank you for your attention.